In this last example, we are told that f is a function defined on the closed interval from 0 to 6, and we are given the graph of f prime, the first derivative. So we will often have to answer questions about intervals of increase or decrease based on a graphic representation of f prime instead of through function analysis. So on the one hand, there's things about this that are easier. We don't have to find a complicated derivative. On the other hand, something that is more challenging is that our eyes and our brain want to trick us very often into thinking that our graph of f prime is actually the graph of our function. So we have to remember that even though our graph of f prime informs us about our function f, we have to be really careful not to mistake its attributes or key features with that of the graph of f. Okay, so part A of this example, we are asked on what intervals is f increasing. And while this is optional, I will tell you it helps me a lot to still kind of think of the same number line we've been drawing. So I know that I want to think about any spot on my number line where my derivative f prime is either non-existent or equal to 0. And there's no spot where my derivative does not exist between 1 and 6. There is, however, one place where x is equal to 3 where my derivative is 0. So I am going to just put 3 on my number line. And if I look at all of the values of f prime between 0 and 3, all of those values are positive. So f prime, and you know what? I started this as a number line that goes on forever, but really this number line is from 0 to 6. So f prime is positive on the interval from 0 to 3, and f prime I can see is negative from 3 to 6. So that tells me about f. I know between 0 and 3 f is increasing, between 3 and 6 f is decreasing. So on what intervals is f increasing? I could answer that and say f is increasing on the interval. Now I'm going to write the open interval from 0 to 3, because at 3, f prime 0, so f is not increasing or decreasing, but also we always use an open interval. Technically, even though f prime is positive at x equals 0, if I don't know what's happening to f, or if the domain of f begins at 0, I wouldn't really say that f is increasing at 0. But f is increasing on the interval from 0 to 3 because f prime is positive, or f prime is greater than 0. Now, just to go back to what I said, if you were to use a bracket here instead of a curved bracket, it's not like going to be counted wrong. I would just err on the side of using open intervals when we talk about intervals of increase and decrease. In part B, at what value or values does f have a relative maximum or minimum value, and to justify our answer? Well, again, using the same number line we drew, we could see that our only critical value is where x is equal to 3. And that since f prime is changing from positive to negative, we have a maximum. So f has a relative or local maximum at x equals 3. And that is because f prime changes from positive to negative at x equals 3, at x equals 3. In part C, we are asked to evaluate the second derivative. So we are asked to evaluate the second derivative at x equals 3. And I'm going to erase some of the highlighting that I put on here. If you're following along and you highlighted your text that color, you can leave it, obviously. We'll just write next to this. If I'm evaluating the second derivative at 3, given my first derivative, I can only do that because the piece of f prime that includes x equals 3 is linear. So I know my second derivative is my instantaneous rate of change of my first derivative at 3. So what I really want here is the slope of this line segment that includes x equals 3. So I could see that I'm going down 4 units as x increases to the right 2. So my slope there is just -2. So my second derivative of f at 3 is -2. And in fact, my second derivative is -2 from but not including x equals 2 up until but not including x equals 4. Remember that our second derivative will be undefined at x equals 2 and x equals 4 because the graph of f prime is not locally linear there, or in other words, we might say that we have corners there. And that actually rolls us right into part D, where we are asked to sketch a graph of y equals our second derivative of f. So again, I want to point out that f prime is defined on this closed interval from 0 to 6. We don't know anything about f prime before 0 or after 6. So for example, I don't know if f prime even exists before 0 for values of x less than 0. And if it does, I don't know what it's equal to. Like, it's possible that I could have a corner at 0 as well. So when I'm sketching the graph of of my second derivative, I kind of want to look at this piece by piece. And I could see that this first piece right here from x equals 0 to x equals 2 is linear. And the slope of that line segment is +1/2. So down here, when I go to graph my second derivative from 0 to 2, but not including x equals 0 or x equals 2, my second derivative is 1/2. So I'm going to estimate 1/2 on my y-axis. I'm going to use an open circle. And from 0 to 2, my second derivative is just 1/2. Now again, we said that at x equals 2, f prime is not locally linear, meaning our second derivative is non-existent there. But from x equals 2 until x equals 4, excluding those values, we said already that in part C, that our rate of change, instantaneous rate of change here, or our slope, is -2. So on my graph of the second derivative, from 2 to 4, but excluding those values, my second derivative is -2. All right, finally, for that very last piece, from x equals 4 until x equals 6, but not including 4 or 6, we have a slope of +1/2 again. So from 4 to 6, but excluding those endpoints, our second derivative is equal to 1/2.